Welcome to the session. Myself, I am Shravani, Assistant Professor from the Department of CSE. Today I am going to discuss Quicksort under Unit 2. So today we will discuss the Today we will discuss the concept of Quicksort followed by algorithm. There are two algorithms. One is Quicksort algorithm and the other is Partition algorithm, followed by an example, followed by analysis. We will see today. Now, the main objective of today's lecture is the students are able to understand the concept of Quicksort. Now, the outcome is the students are able to apply the Quicksort on a list. So, what is meant by Quicksort? Why the name is Quick? So, now we will see with a real-time example why this name came, right? So, let us take, there are students, certain number of students in a classroom with a certain height I am showing here. So, these are the students I am having in the classroom. So, for suppose here I want to arrange these students according to their height. So, generally there are two options to arrange them. The first option is the teacher will call each and every one of them by means of their roll number or by means of their name, and she is telling the position, you stand in the first position and you stand in the second position. Likewise, the teacher will assign, and the second option is students themselves they can arrange, right? So, you yourself arrange. Likewise, also the teacher can ask you, right? So, these are the two options. The first option is done by the teacher and the second option is doing by themselves, right? So, if I want them to arrange themselves, then how they are going to be arranged? That is, so here this person is a very little guy, right? So, this little guy, he knows that I am a very short person among my classmates. So, myself I will come to the first position. And he also knows that I am the tallest person in the classroom. So, I will stand at last position. So, the remaining themselves they will arrange according to height, right? So, this is what. So, here if you have seen clearly, there is no temporary array, like there is no temporary array which we have used in the merge sort. Here in place, that is within their places only, we are swapping, we are applying the swapping procedure. That is, they are exchanging themselves and they are set writing in the correct positions, and in those positions they are standing, right? So, this Quicksort is all now which uses in place concept, nothing but. Okay. So, now we will see what is meant by Quicksort. We will see what is meant by Quicksort, which is an efficient algorithm. Exchanges occur in between the elements. Okay. So, here exchanges occurs in between the elements that are far apart, and these exchanges are needed to place an element in its final position. That is, here we are going to select an element which is pivot element. That pivot element can be taken either the first element or the last element or the middle element. Any of the element we can take it as a pivot element. Okay. Now, basing on the pivot element, we are going to apply some partition procedure such that here whenever I am calling that partition procedure, so it will returns me the pivot position, nothing but pivot location. So, after making a certain order, what happens is here the elements which are prior to the pivot are lesser than the pivot, and the elements which are greater than the pivot are after the pivot, are placed after the pivot element. In such a manner, we are going to place our elements in the Quicksort. Coming to the procedure, first of all, here myself I am taking the first element as a pivot, but some textbooks or some material says that you can take the pivot element as a last element, or you can take pivot element as a middle element. Whatever the element, okay, whatever may be the location, you can take any one of the element as a pivot element. But for my concept, I am taking the first element as a pivot. Now, based on the pivot element, the list is divided into two halves in such a way that here the elements in the left are smaller than the pivot and the elements in the right half are greater than the pivot. Here the elements which are left to the pivot are smaller and which are right to the pivot are greater, which I mentioned you previously. Create two sublists. So here whenever I am making the pivot position in a correct position, so after that what happened? Here again I have to apply the DNC procedure such that I will be having again two more lists. One is left sublist and the other one is right sublist, because the pivot is already positioned in the correct place. So I have to take again the left sublist and right sublist, that is from starting position to pivot -1 and pivot +1 position to the last one. So likewise I need to take and I need to apply the quicksort again and again until the entire list is sorted. Now, so here A of low to A of pivot -1 is one list, A of pivot +1 to high is another sublist. Now the left and right sublists are sorted again using the quicksort algorithm. So this is a basic procedure used in the quicksort, and the name is quicksort but the performance is low. Nothing but here the operation is being done quickly, right? They are placed quickly, that's why it is quicksort. But actually the time required to do this quicksort is more. That we will discuss later. Now this is the basic algorithm used in the quicksort. So here I will be having three parameters: array, which is a given list, and low is the starting index and high is the ending index of your array. Now here I am going to find out the pivot location by calling the partition procedure. As I said earlier, here I will call the partition procedure, and that partition procedure will give you the exact location of pivot by exchanges, all the exchanges and all the swappings. It will positions correctly the pivot, it will places correctly the pivot element, and it will returns the final pivot location. Now after getting the pivot location from partition procedure, we are applying the quicksort from low to pivot -1, and again we are applying the quicksort procedure from pivot +1 to high. That is for left list and this is for right list of your pivot. Okay. So here this partition algorithm clearly places the pivot element in the correct place. That is the main theme of this partition procedure. After that we are calling the quicksort algorithm again for left list and again for right list. This is the internal procedure of partition algorithm. First step is to compare the pivot element with A of I. Compare the pivot element with array of I. Initially array of I points to the low. Now if array of I is less than the pivot, then if it is less than the pivot, what we have to do? Increment the I, otherwise stop I. Now the variable I always moves from left to right. Please remember, the variable I is always moves from left to right, whereas the variable j is existed, the j will always move from right to left. Okay. Now next, coming to the step 2. Here in the previous step we are comparing A of I, right? Now in the next step we are comparing A of j. So here array of I is less than the pivot, we are incrementing the I, right? So here we are checking array of j is greater than the pivot, then decrement the j. Okay. Here I is moving forward, which is a forward pointer. J is a backward pointer, right? So I we are incrementing I plus plus, and j is we are decrementing j minus minus. So I, whenever we are incrementing I, if A of I is less than the pivot. Now here if A of j is greater than the pivot, then we need to decrement the j value. Coming to step 3, if I is less than j, then swap array of I and array of j. Swap array of I and array of j. Exchange both array of I and array of j and increment the I value and decrement the j value. And else, that is if I is not less than j, that is if I is greater than j, there is no need of any exchanging of A of I and A of j. Coming to step number 4. When variable I becomes more than j, that is when I is greater than j, at that case swap array of j with pivot element. Swap, finally there is an exchange from array of j to pivot element. Hence the pivot is positioned at the correct place. So here finally when the value of I becomes more than j, that is greater than j. So in that particular situation, swap array of j with pivot. Hence the pivot is placed in the proper place. So initially what we are doing, we are comparing the pivot with array of I. Now if array of I is less than the pivot, if array of I is less than the pivot, then increment the I, that is nothing but I plus plus. Now, and one more thing, I is a forward pointer and j is a backward pointer. Now, here in the step number 2, we are comparing pivot with array of j. Now whenever we are comparing with array of j, so here array of j is greater than the pivot, in that case decrement. Now finally j is always moving from right to left. Now step number 3, if I is less than j, then swap array of I and array of j. Now partition algorithm, as I said, this partition algorithm is going to give you the exact location of pivot, right? So now what is this partition? So here basically this partition algorithm takes 3 parameters, array, low and high. I is equal to low plus 1. Here I am starting with the low plus 1. Why? Because here I have taken the first element as a pivot element. Pivot element means here low element. A of low I am taking it as a pivot element. So that's why the I starts from the next location of your pivot. Now j is equal to high and pivot is equal to array of low. J pointing to the last location and I points to the pivot next location, as a pivot is a first element. Now pivot is equal to array of low. Now while I is less than or equal to j, what we are having to check, array of I is less than pivot and I is less than high. If array of I is less than pivot, here the main funda is the pivot, if the pivot is here, so here this list must be less than the pivot and here this list should be greater than the pivot. That is a basic principle. That is, here whenever we are making partition, here pivot must be in the middle and the left elements to the pivot must be less than the pivot and the right elements to the pivot must be greater than the pivot. So that's why if array of I is less than pivot, so this is correctly placed. So here just we need to make I should be incremented. Now while array of j is greater than pivot, so which means that elements are also in the correct position. So just we need to decrement the j. Now if I is less than j, so in that case swap array of I and array of j, and finally I plus plus and j minus minus, because I is a forward pointer and j is a backward pointer. Now else I plus plus. Now finally array of low to be array of j and array of j to be pivot, because this is a final exchange. So that I will be returning the j. J is nothing but pivot location. Okay. Now this is the algorithm for partition. So let's see an example. So here this is an example. Here I am showing the pivot element in yellow color and I is in blue color and j is in red color, okay, for your identification purpose. So here 48 I have taken as a pivot element and 44 is pointing to I will points to 44 and j will points to 68, because initially I value is low plus 1 and j value is high, right. So now what happens? Now 44 is compared with 48. Now 44 is compared with 48. So as a 44 is less than 48, I will points to the next location, which is 19, and j remains in that position. Now again the array of I is 19. 19 is again checked with pivot. So here 19 is again checked with pivot, which is 19 is less than 48. So now what I have to do? I plus plus. Now I will points to 59. Now again here is my pivot and here is my j. Now again 59 and 48 both gets compared, right. Now here 59 is greater than 48. So what I am supposed to do in this particular thing? So now coming to j, okay, as a 59 is greater than 48, j should be decremented. Now j value is 95. Now j points to 95. Here I am showing you. Now again 59. Okay, now again 59 and 48 gets compared. Now again 59 and 48. Now again 59 is greater than 48. Now again j has to be decremented. What is the j value now? J points to number element 8. Now here we need to stop, because here stop I at index 3 and j at index 9. If I is less than j, what I am supposed to do? I have to swap I and j. That is 59 and 8 get swapped. Now 8 comes over here. Now again I have to increment the I value. Now I points to 72 and j points to 82 and pivot points to 48. Now again we will have a comparison. Now again we need to decrement the j value. Now again we need to decrement the j value, right? Now again we need to stop over here. Why? Because here if I is less than j, so here swap I with j. Now again I and j both are pointing to the same location, that is 80. Now after that again 80 and 48 gets compared, right? So here j will be decremented according to that case and I will be incremented. Now we will see the next iteration. Whenever j exceeds I, then we need to swap a of I with the pivot element. So now what happened finally? This 48 will comes over here and this is my half list and this is my remaining half list. So now what happens? So the list of elements which are left to this 48 are all less than 48, and here the elements which are right to this 48 are greater than 48. So this is subproblem 1, and this is subproblem 2. Now again these two subproblems are going to be solved again by applying quicksort. So in that again I will apply the partition procedure repeatedly. Finally I will be having the final sorted list. Now we will see that procedure. So now 48 as a pivot element. So this 48 is placed in the correct position. So then I will be having left list as one list and right sublist as one list. Now again for the left sublist again I will apply the pivot as a 42. And again 44 is pointing to I and j points to 8. Now again here in this manner the quicksort procedure again it is going to be applied, and finally I will be having the sorted list, left sorted list as 8, 19, 42 and 44 as shown here, and the right sublist as 59, 65, 68. So in the same manner I will apply the quicksort procedure even for the right sublist. So then I will be having the sorted list for right sublist, and finally I will be having the final sorted list. Now let us see the analysis part. So for the best case or average case, so the quicksort would be when we get two lists are of equal sizes. So are of equal sizes or mostly equal sizes, then this best and average case will be taken into consideration. So if we have n elements, then the size of two sublists is approximately equal to how much? N by 2 size, which are always divided equally. So we get 4 sublists of sizes approximately n by 4, and again that n by 4 again they will be divided into approximately equal to n by 8, right? So again here 8 sublists of sizes n by 8. So likewise we'll be having the division of sublists. Now the n elements are repeatedly divided into half approximately log n times. So here the n elements are repeatedly divided into half. Even for the left sublist also it gets repeatedly divided into half. Even for the right sublist also it gets repeated into half, right? So now the total number of comparisons made are n plus 2 into n by 2. Why this is 2 into n by 2? Why this is 2 into n by 2? Here n elements, okay, if you have n elements, then the size of two sublists is n by 2. Then the size of two sublists is n by 2. Then which is 2 into n by 2. Now again if I am having 4, then 4 into n by 4, and again 8 into n by 8, and so on n into n by n. So finally how many n's I will be having? N plus n plus n, so on n n's I am having. So here all the n elements are repeatedly divided into what? Half. Approximately how much number of time? if it is dividing for n times, so which is log n. So finally n log n is a complexity for best and average case. Whereas for the worst case it is big O of n square. For the worst case it is big O of n square. For the best and average case, which is big O of n log n average. Then what will come under worst case? So for suppose the given list itself is a sorted list, then on that sorted list we want to apply the quicksort procedure, that is come under worst case. So for that it will take big O of n square, okay, which is a very time taken, right, compared to n log n. Let's come to a gate question. Let P be a quicksort program to sort numbers in the ascending order using first element as a pivot element. So whatever we have taken till now, first element as a pivot element, and T1 is the time required for the number of, for the input P is equal to 1, 2, 3, 4, 5. So here this is one list and this is one list. So T1 is a time taken for list 1 and T2 is a time taken for second list. Now which one of the following holds correctly for the given problem instance? So these are the options. T1 is equal to 5, T1 is less than T2, T1 is greater than T2 and T1 is equal to T2. So which one suits for this particular problem? Time required for the first list. First list is 1, 2, 3, 4, 5, which is already in sorted order. And whereas the second list is 4, 1, 5, 3, 2. So which one takes more time? As I said earlier, in the worst case it takes big O of n square, right? N square time it takes. Worst case means the list is in the sorted order, right? So finally T1 is greater than T2 because as the first list is in sorted order, it takes more time as it come under worst case than for the second list. So T1 is greater than T2. Once again you can see the explanation I am showing you now. This is the explanation. When first element or last element is chosen as a pivot, the quicksort worst case occurred for sorted arrays as big O of n square. So now here the recurrence relation for that such case is T of n is equal to T of n minus 1 plus big O of n. So finally the final answer is, as I said earlier, this is T1 is greater than T2. The time required for the first list to apply quicksort is greater than the time required for the second list. Let's have a summary. So today we have discussed what is meant by quicksort and how the quicksort is applied on a given list, and also we have seen quicksort algorithm, partition algorithm followed by analysis. This is a small exercise. So apply quicksort on this given list.